And then from here, it's a little bit easier to simplify. So notice that now we're going to have Rn equals, when you multiply these, we'd end up with 1 over n to the power of 3. And then notice this here, 1 squared plus 2 squared all the way to n squared. That's actually a series. It's a certain sum, and there's certain fundamental series that you have to know that I'm going to keep bringing up in this section. So for example, let's say that you're adding from 1, 2, 3 all the way to n. Well, that series, the fundamental formula for that is n times n plus 1 divided by 2. However, notice it's not this, we're squaring each number, and there's actually a formula for that too. So if you are taking 1 squared plus 2 squared plus 3 squared all the way to n squared, whatever that number is, the formula for that is n times n plus 1 times 2n plus 1 all over 6. Right, and there's going to be other formulas that we may use throughout the unit as well, and if we do need them, I'll continue bringing them up. But you have to know these formulas. So here, for this square bracket, we could sub in this formula over here. So what I'm going to do is I'm going to write n times n plus 1 times 2n plus 1, and then all of that is going to be over 6. So I took this and then converted it to that. And then from here, what we can do is simplify further. We're just going to basically multiply these two terms. So notice that we have an n up here. We got 3 n's down here. So this would cancel out with this. We'd be left with 2 n's at the bottom. Then we could just multiply the numerators and the denominators. So basically, Rn would end up equaling n plus 1 times 2n plus 1. And then we'll have 6 times n squared. Like that. And so this here ends up being the general expression for Rn, which is really nice because what this is going to give us is the sum of the areas of however many rectangles we choose. We could pick any n here and we just have to plug it into this formula. We have a general formula now. So if you remember the first example we did, we used 4 rectangles. So what would happen if we plug in 4 for all of this? Well, notice this bracket would end up being 5. This bracket here would end up being 9. And then we'd have 6 times 4 to the power of 2. And then notice that the 9 over 6, that would simplify to 3 over 2. Sorry, I put a 3 there. Right? And so what would this be? 5 times 3, 15. 4 to the power 2, 16 times 2, 32. And if you remember, 15 over 32 is what we got for R4 when we did it manually. But notice now we can just get it right away because we have that general formula. What about R5? Because we also did an example with 5 rectangles. So what would happen if we plug in 5 for the brackets here? Well, notice we'd have 6. Over here we'd have 11. And then we'd have 6 times 5 to the power of 2. Notice the 6's would cancel out. We'd be left with 11 over 25, which is what we got when we found R5 before as well. Right? So it's nice. We don't have to go through and find R4 manually and R5 manually. We just have to find this general expression, which does take a lot of work itself. But now we can just get those values quickly. And then we could get whatever values we want. So we can get the value if we used 100 rectangles. We could just plug in 100 for n. And that's, remember, when you're using more rectangles, that's going to give you a better approximation. And so the question is, how can we get an exact value? Well, if you think about it, as we said, the more rectangles we use, the better the approximation is going to be. And so the exact value or the exact area is going to happen when this n approaches infinity. as we use an infinite amount of rectangles, these spaces that are here, these like excess spaces, they're going to be so minimal. Those are going to approach to 0, and we're going to get an exact approximation for that actual area under the curve. So the exact area is basically the limit as n approaches infinity of whatever your Rn is going to be, or your Ln. I'm going to go through deriving the Ln formula. Though it's not as important, you basically just have to derive one of them, and usually the Rn formula is easier to derive than the Ln. So no matter whether you approach an n value of infinity for Rn or Ln, you're still going to get that same exact value. And I'll show you how when we cover the, when we find the Ln formula. But just using the Rn formula for now, basically, if we find this limit, that's going to be the exact area under the curve. And so let's do that now. So what we can do is the exact area is going to be the limit as n approaches infinity of this expression here. So n plus 1 times 2n plus 1 all over 6n squared. And so notice that this here, it's actually a limit at infinity. And so to solve it, what I'm going to do is I'm actually going to expand these brackets here. So you don't have to necessarily. I'm going to just expand them because it's only 2 brackets. So we would end up with 2n squared plus 3n plus 1 all over 6n squared. And then what do? You divide everything by the variable to the power of the highest exponent in the denominator. So I'm going to take everything and I'm going to divide it by n squared. So we would have the limit as n approaches infinity of 2 plus 3 over n plus 1 over n squared all over 6. Notice this is going to go to 0. This is going to go to 0. We're going to be left with 2 over 6, which gives us 1 over 3. All right, so that there is actually the answer to this question. That's actually the exact area. All right, not an approximation, but it's the exact area. Right? Again, as a review, the exact area, the limit as n approaches infinity of Rn or Ln, whichever those expressions that you get. All right, so what if we were to find an expression for Ln like we did for Rn? Now, really, if you're going to be finding this exact area, you only need one of them. You only need Rn or Ln, and Rn is usually the one textbooks show how to get, and it's usually the easiest one to get. But just in case it's asked for, let's find an expression for Ln as well. So what we're going to do is draw out the curve again. So we're going to have an x value of 1. And what we're going to do is split up, okay, into n intervals. So these are going to be rectangles here. This is going to be the last rectangle. But because we're dealing with L now, what that means is that each of these rectangles, these points are going to be on the left corner of each rectangle. So we know that it's going to, the first rectangle is going to be here. The next rectangle is going to be here, right? And then this last rectangle is going to be there, right? So there's going to be n of these rectangles. So from 0 to 1, what's each interval going to be? What's the length of each rectangle going to be? Well, the length is still going to be that 1 over n. Right? It's always basically this number minus this number divided by the number of rectangles that you're using. Right? So 1 over n is basically the length of each rectangle. So notice that the height of the first rectangle is going to be 0. What's the height of this second rectangle going to be? Well, this x value here is 1 over n, so it's going to be f of 1 over n. So let's start making an expression here. So ln would be 1 over n, the length of that first rectangle, and the height of that first rectangle is going to be 0 to the power of 2 when we plug in 0 for the function that we're working with. Then the next rectangle, 1 over n, and then we're going to plug in 1 over n into the function, so we would have 1 over n to the power of 2. And then we're just going to keep adding all the way to this rectangle over here. And this last rectangle, we know, it's going to have a length of 1 over n as well. But what's the height going to be here? What's this x value over here? Right? So we know that this x value is 1. So what's this x value going to be? Well, if you think about it, it's just basically 1 minus 1 over n, because this is 1 over n. So it's like n over n minus 1 over n, which is just n minus 1 over n. That's what this x value here is going to be. And so to get this height here, basically the height of this point, we have to plug in this x value into that function. So it's going to be n minus 1 over n to the power of 2. So that's pretty much the biggest difference between ln and rn. Remember, with rn, the last term was n over n. It was actually this 1 here, because that ended up being the height of that last rectangle. But because now we're dealing with the left corners of each rectangle, the height of this last rectangle is going to be the height of this point, which happens at this x value. Right? So it's going to be a little bit different. So what's going to happen here? Well, notice that this is going to go to 0, right? 0 squared times 1 over n, that's going to be all 0. So we would have what? 1 over n. And then over here we would have 1 squared over n squared, plus, we're going to skip a bunch. Now the next one, we know it's going to be 1 over n, and it's going to be 2 squared over n squared. So I'll just write that. Right, that next rectangle, and then we skip a bunch to the last one, and then it's going to be 1 over n, and then we would have n minus 1 squared all over n squared, like that. And like we did with Rn, what I'm going to do is I'm going to factor out a 1 over n because it's common in all of them, and I'm going to factor out a 1 over n squared because it's common in all of them as well. So what would we be left with? We'd be left with 1 squared plus 2 squared plus all the way to this n minus 1 squared. Right? So instead of going up to n squared like Rn went up to, ln is going up to that n minus 1 squared.